Hello. In this video, we're going to look at using exponentials to solve some word problems. Let's start with a relatively straightforward one. Here we have a bacteria culture that starts with 3 bacteria, and the bacteria double every hour. How many bacteria are there after 1 day? Now, to solve this question, we're first going to convert that 1 day into 24 hours. So that means there's going to be 24 periods of doubling. That means first we start with 3 bacteria, then we double and get 6, then we double to 12, then 24, then 48, and so on. Now, we could just write this out, doing every hour another doubling, but we could also use exponentials, because what we have is a beginning with 3 bacteria, and then we multiply by 2, because 6 is 3 times 2, or we multiply by 3 times 2 times 2, or 3 times 2 squared. 24 is 3 times 2 cubed, and 48 is 3 times 2 to the 4. So what we're doing is we have 3 times 2 to the power of x, where x is the number of hours since we started monitoring our bacteria culture. In that case, we would have 3 times 2 to the power of 24, which if we worked it out on a calculator would be 50,331,648 bacteria. This goes to show why you might get sick relatively quickly. If you go to bed with a bit of a sore throat and wake up with a full-blown infection, it's because those bacteria are doubling every hour. So during the 8 hours while you're sleeping, it goes from a colony of a few thousand bacteria that you can just barely begin to feel to a giant infection with millions or potentially tens of millions of bacteria that your immune system has to fight. Now, in this situation, it was a little tricky because you have to come up with the formula yourself. And generally speaking, for these first few we're going to look at, we're going to develop the formula ourselves. On a quiz or on the final exam, they often will give you the formula and annotate it. And we'll look at some examples like that. But to start off with, I really want us to develop these formulas and then to solve them ourselves. Let's go ahead and look at this example. Cobalt-60 has a half-life of approximately 1 year. If the sample starts with 100 grams, how much sample will remain after 5 years? Cobalt-60 is a radioactive element, which means that it gives off radiation and that reduces its mass. And so the half-life means that after 1 year, approximately half of the substance will be left radioactive. And then after another year, half of that will be left. So you start off with 100 grams. That's radioactive. After 1 year, you'll have 50 grams. After another year, you'll have 25 grams. And another year, you'll have half of that, which is 12.5 grams. And so each year you have half as much of the substance left. So again, we can model this with the equation y equals 100 times 1/2 to the x, where x is going to be measured in years. Then we simply plug in 5, and we use a calculator to get 3.125 grams. Now you probably could have come up with that number if we would have done just a few more steps above by hand, but what if you had to wait for 30 years? If you're wondering how much of the substance would be left after 30 years, in this case, you really would want to use that formula because you wouldn't want to do this 30 times. So again, we go 100, 1/2 to the power of 30, and then we go ahead and type this in. And your calculator is probably going to give you a weird number like 9.313 times 10 to the negative 8 grams. What this means is there's going to be 1, 2, 3, 4, 5, 6, 7, and then the 9. So 1, 2, 3, 4, 5, 6, 7, 8. This is the number if we wrote it out without scientific notation, and it means that there's pretty much none left. In our example with the cobalt-60, after 30 years, there's pretty much no radioactivity left in the sample. All right, why don't you go ahead and try this example on your own. We have movie tickets that cost $15, but due to inflation, the prices rise by 2% each year. how much will the movie ticket cost in 30 years? All right, hopefully you gave this one a try. And to do an increase of 2%, well, we would take that 15 and we multiply it by 1.02. The 1 stands for the original price, and the 2 represents the increase. So if we did 15 times 1.02, that would give us 15.30. That would be the cost of the movie after 1 year of inflation. But of course, inflation keeps going year after year. And so in 30 years, we are going to need a formula. $15 times 1.02 to the power of x, where x is years. Let's go ahead and plug in our 30. And so we get $64.83. Now, that's a pretty expensive movie, but you know, maybe the theaters are better in 30 years. Maybe there's 3D or even, you know, those chairs that shake as the movie happens. Maybe you have even more surround sound. Who knows? Maybe the movies are really worth it in 30 years to be paying $64. But inflation isn't just about things like movie tickets. It also includes things like houses. So let's say your house, which is worth $300,000 right now, how can we figure out the cost of your house? Well, again, we changed the number in front, but it's still going up at 2%. So we have 300,000 times 1.02. And then, of course, we're going to raise that to the power of x equals 30 years. So in this case, we're going to get $543,480.48. So that's pretty rough. In 30 years, meaning when maybe your children are looking at buying houses once you've grown up and had children of your own, they're going to be paying almost double the price that you would have paid for a house. And so hopefully they're making twice as much money as you, otherwise it's going to be pretty tough for them to afford a house. And of course, these numbers get a little scary if inflation gets out of control. 2% is what the government hopes for inflation, but recently we've seen numbers as high as 6% inflation or even 8% inflation. Now, I don't want to scare you too much, but we could just change this question to take our $300,000 house, and let's say inflation continued at 7%, so 1.07 to the power of 30. Then you plug in your 30 years, and in this case, you end up with 2,283,676.51. In other words, when someone wants to buy a house in 30 years, so maybe your children, they won't be spending $300,000, they'll be spending $2.2 million. And again, not to scare you because this isn't necessarily a problem for you, it's more a problem for future generations. This is why the government gets concerned about inflation, why they try to bring up the interest rates, and why generally inflation at 6, 7, 8% is not a good thing for society, because they make it really hard for future generations to afford necessities, the basics of living, things like food, shelter, and clothing. Now, the opposite of inflation is deflation. So vehicles tend to depreciate with an average of, let's say, 15% per year. So if you buy a $20,000 car, how much will it be worth in 6 years? So to do depreciation, it's kind of the opposite of inflation. We take 100%, which is the original value of the car, and we subtract off 15%, which gives us 85%. So we can take that $20,000 car and multiply it by 0.85. And that will tell us the cost after 1 year, or the residual value, $17,000. So you've lost $3,000 of value. But of course, you keep losing value with cars. When you have that new shiny car and it's initially, so valuable at $30,000, eventually some wear and tear, some nicks and some dents, that car is only going to be worth, 17, 15, 10, 5. Eventually the car is worth only scrap, next to nothing. So let's see what happens after 6 years. We take our $20,000, multiply by 0.85 to the power of x. X will be 6 years, so that gives us 20,000 times 0.85 to the 6, which will work out to $7,542.90. Let's look at another problem, this one dealing with a virus. A virus has an R0 value of 5. That means on average, an infectious person infects 5 other people. The pandemic begins with 20 infections, and they infect others once per week. How many people will be infected after only 9 weeks? Well, this is a bit of a disturbing example given the pandemic that we had, but it is interesting to try to do the math of this and to understand why pandemics can have this exponential type growth. So we have 20 people who are infected, and each person infects 5 others, so you take 1 plus 5. 1 for the initial person who's infected and 5 additional new people to the power of x, where x in this case will be weeks. So we plug in our 1 plus 5, or 6, to the power of 9 weeks. And using our calculator, we get 201,553,920 infections. Now, an R0 value of 5 is quite high, but not unreasonable. And you can see here how after only 9 weeks, a pandemic that begins with just 20 people can quickly infect hundreds of millions. This is generally why scientists and medical professionals recommend things like quarantine, things like social distancing, and other mechanisms to try to bring that R0 value down. The less interactions people have, the less likely they are to pass on the infection, and hopefully the spread can be, if not stopped, at least slowed down, because 200 million people being infected in 9 weeks would be very challenging. Let's look at another example, this one with computers. So TPUs, or tensor processing units, are used for AI, and they're doubling every 2 years. The current TPU can process 393 TOPS, or tera operations per second. How fast will the TPUs be in 4 years? Well, we take the 393, multiply by 2 to the power of, and you might think x, but it's doubling every 2 years, which means you need x over 2. Here, x is the years. Because if you plug in 2, 2 divided by 2 is 1, so you only have 1 doubling. Or 4 years is 4 divided by 2 equals 2, so 2 doublings. So now we go ahead and do 393, 2 to the power of 4 over 2. Make sure on your calculator, depending on the one you have, you might have to put this exponent in brackets itself. So it types in properly, and you should get 1572 TOPS, or tera operations per second. Now this question is a little different than the other ones. We're given the equation and we're explained what each piece does, but we're asked to then plug in the values and calculate. So we're told that we have 7 years, we're going to invest $100, the interest rate is 13%, and it's compounded continuously. The formula will be A equals P e to the RT. A is the final amount, P is the principal, R is the interest rate, and T is the time. So let's see if we can find each one of these values. 7 years, that sounds like the time. $100, that sounds like the principal. 13%, yep, that's the interest rate. So we're just looking for the final amount. That means A equals 100 e to the power of, well, the interest rate is 13%, so we should put that as 0.13. And the time is 7 years times 7. Now again, on your calculator, you might need to put that power in brackets just so it works out properly. You should get $248.43. Now let's do another one, and you can go ahead and pause the video, try to plug in the numbers yourself, and see what you come up with. All right, so let's see what information we have. We want to have $100,000, so that's the final amount. We have 40 years to work with. That's the time. 6.5% is the interest rate. Let's go ahead and plug in our numbers. So $1 million equals P e to 0.065 times 40. Now this question is a little bit different because we can't just hit equals. We're looking for the value p. So a little bit of algebra is going to be needed here. I guess we could do it right at this step. We could divide both sides by e to the 0.065 times 40. E to the 0.065 times 40. It's going to give us p equals, and now be very careful on your calculator. When you divide it, you might need to put brackets depending on the calculator you have, and again, you might need to put brackets for the exponent. But assuming everything types in correctly, you should have $74,273.58. So what this says is if you want to be a millionaire by the time you retire, all you need to do is come up with $74,000, invest it, and you'll be a millionaire. It's kind of an interesting thought process here. Rather than working hard, making a company, or doing something super fantastic, all you need to do is put away $74,000, which maybe at your age seems pretty tough. But if you work a couple summers, get a part-time job, you could easily save, $5,000 to $10,000 a year. If you saved $10,000 a year times 7 years of working, that would give you your $70,000. If you were 18 when you started this process and you added 7 years, that would put you at 25. 40 years later, it would put you at 65, and you would be a millionaire when you retire at the ripe old age of 65. Now, is this possible for everyone? No, some people have to pay for school and they have other expenses, but it certainly shows you the power of compound interest. All right, here's another question, and I want you to pause the video, try to read the question, and see what you can come up with. All right, so a marketing team uses a complicated exponential function to model the probability that a customer will make a purchase based on the amount of time they spend on a website. This is the function. P of x is the probability, x is the minutes they spend on the website. Determine the probability they will make a purchase if they spend 30 minutes. Well, it looks like this 30 is going to be our x value, so we need to plug that in over here. That's going to give us P of 30 equals 1 over 1 plus e to the negative 0.2 times 30 minus 3. Again, this question is not particularly difficult from a math perspective, but it is tricky to make sure that all the numbers get plugged in correct on your calculator. Once you crunch the numbers, you should get 95.257%. If you're wondering why I'm doing 3 decimal places on this question and 2 on the other questions, when you have money, you always go to 2 decimal places, but for everything else, we go to 3 decimals. And this means that if somebody spends 30 minutes on a website looking at products, it's pretty likely they're going to hit that purchase button. They're more just trying to decide which product is their favorite, but I mean, come on, if we've been looking at the same page for 30 minutes, unless we accidentally left our computer open, we're probably going to be buying something. Here's one more, and again, I encourage you to pause the video and give it a try. All right, well, we have the following information. The carrying capacity is 500. That looks like K. The initial population is 100. That's P0. The growth rate is 0.1 per year, so that's our R. And the time is 5 years, that's our T. So it looks as though we're good to go. We should be able to plug everything into our formula. So P of 5 equals 500 divided by 1 plus 500 minus 100 over 100 e to the power of negative 0.1 times 5. And when you work that out, you should have 145.938. Now, in this case here, we have to be a little careful. We're talking about rabbits. This is a function that models the growth of rabbits, and you can't really have 0.938 of a rabbit. So the question is, should we round up? Should we round down? It sort of depends on the context, but in this case, I think writing it as 145 rabbits would make the most sense. We don't have a whole rabbit at the end there, And while it might be tempting to say we have 146 rabbits, we haven't quite gotten to that last rabbit. So I would just write the whole number on its own and ignore the decimal, saying 145 rabbits. Now, if you're looking to take some notes on this, it's kind of a tricky thing to do notes on because each question will be different. But basically, let's say you had A equals P to the ERT. If that was your formula and I told you A equals 300,000 and R equals 9.5%, T equals 20 years, and you have to solve for P, basically it's just algebra with the added techniques that any kind of percent needs to be converted by dividing by 100. So you get 0.095. You need decimals instead of percents when you plug it in. Anytime you see something like an E, you want to use the E button on your calculator so that you have that nice exact, not just the 2.71. And make sure you reread the question multiple times so that you're plugging in all the values correctly and you're not missing anything from the question. But let's go ahead and solve this one real quick. We'd have 300,000 equals P e to the 0.095 times 20 years. Again, another thing you might want is that brackets around the exponent, so you plug it in properly. Then, of course, we're going to want to divide both sides by e to the 0.095 times 20, e to the 0.095 times 20, and P will equal 44870.59. Again, here, money is 2 decimal places, so that might be something to look for. Also, you should include the units. Make sure you throw that $sign in front. But otherwise, these questions are pretty straightforward. You can go ahead and give it some practice. Unit 8, Worksheet 8 and 8.5 have some excellent word problems in there, so go ahead and give those a try. Hopefully you enjoyed these questions with solving exponential equations. And as always, thanks for watching.